The next theorem shows a relationship between a prime element and an irreducible element. Okay. Again, D is an integral domain. So in this case, a prime element is irreducible. Okay, let's prove this. Okay, so suppose uh, suppose P is a prime. So by definition, what this means is that if uh, P divides AB, then either P divides A or P divides B. So this is the definition of a prime. And we want to prove it is irreducible. Irreducible means if uh, P divides A, no, I mean A divides P, then either A is a unit or associate of 1 or it's an associate of U, associate of P. So U is some unit. Okay, so suppose P is a prime, and then and also suppose A divides B. So from here we want to show that A is an associate of 1 or P. Okay, so then since A divides P, that means P is equal to let's say AB for some B. Okay, so this means so since P is equal to AB, that means P divides AB. And and since P is a prime, this means either P divides A or P divides B. Okay, so if P divides A, then we have A is equal to PC for some C. And so we put this into this. Then we have P is equal to AB equal to so A is replaced with PCB. So and since D is an integral domain, we can cancel P's. So we have 1 equal to CB. Therefore, B is a unit. So P is AB and B is a unit. Therefore, P is an associate of A. Okay, and if so, we are saying either this or this, so we have to consider the case when P divides B. So if P divides B, then B is equal to PD for some D. So we put this into this. So P is equal to AB and B is replaced with PD. But integral domain is commutative, so this is we can swap the order of this product, so AD. And again, canceling P, we have 1 equal to AD. Therefore, in this case, A is a unit, and unit is an associate of 1. So therefore, A is an associate of 1. And we are done. So either this or this. Therefore, A is irreducible. So this theorem shows prime elements are irreducible elements. So prime implies irreducible. But not the other way around in general. But if we consider the integral domain, the set of integer, in this case, every irreducible element is also a prime element. So we don't have distinction between prime numbers and irreducible numbers in the case of the set of integers. And we would like to investigate other integral domains that behaves like the set of integers, in which every irreducible element is a prime element. For that, we introduce the following definition. Okay, here's the definition. Again, D is an integral domain in which every element which is non-zero and non-unit so every non-zero non-unit element of D can be expressed as a product of irreducible elements. Pm. Pi is irreducible. And I is from 1 to up to m. So X can be expressed as a product of finite product of irreducible elements. And if we can express in the same X in another way, let's say Q1, Q2 up to Qn, and Qi is irreducible, and I is from 1 to. So if that's the case, then m is equal to n, and by appropriately ordering these elements, these irreducible elements, we can set Qi is equal to Pi times Ui. Ui is a unit, and I is from 1 to up to m. So that means up to the unit factors, we can express these non-zero non-unit element of D as a product of irreducible elements in a unique manner. If this is the case, then the integral domain D is called unique factorization domain. Unique factorization domain, or UFD. So essentially, an integral domain with this property is called a unique factorization domain. So what this means is that every element of D, if it's non-zero and not unit, they can be expressed as a product of irreducible. So in the case of in the case of integers, then this will be prime number factorization. So we define an integral domain that looks similar to the set of integers in this way, from this aspect. So that is called a UFD. And as a matter of fact, the set of integers is a unique factorization domain. So every non-zero and integers that is not equal to 1 can be expressed as a product of prime numbers. And prime numbers are irreducible. So this set of integers is a unique factorization domain. Now, it turns out there's a nice property in a unique factorization domain. So this theorem says in a unique factorization domain, every irreducible element is a prime. So in a unique factorization domain, the converse of the previous theorem holds. Now let's prove this. So let D be a unique factorization domain, and let X be an irreducible element. And suppose, so to show X is an irreducible element, we first assume X divides AB, and we show that either X divides A or X divides B. So we are going to show prove this starting from this, assuming D is a unique factorization domain. So by assumption, there exists some element y such that xy is equal to AB. Now, since D is a unique factorization domain, we can express A and B and Y as each of them as a product of irreducible elements. So let's say A is expressed as P1, P2, and so on up to Pm, and B as Q1, Q2, and so on, and Qn, and Y is equal to R1, R2, and RT, and so on. So that the expression of AB, YB like this. And these are irreducible elements. Then we substitute these into this. We have x is equal to r1, r2, rt, and p1, p2, pm, q1, q2, qn. But this is two different expressions of the same element. So, and x is irreducible. So considering the number of irreducible elements on the left hand side and the right hand side, we have 1 plus t is equal to m plus n. And also each element on the right hand side is an associate of one of the elements, at least one of the elements of the on the right hand side. So therefore x is an associate of one of these, p1 to pm and q1 to qn. So that means x is one of the factors of either a or b, either a or b. So this part is c, this part is b. So therefore x divides a or x divides b. So therefore x is prime, and we are done. And let us define divisors and the greatest common divisor of in an integral domain. Again, D is an integral domain. Then we say, okay, and let A, B, C be non-zero elements. Okay, we say C is a common divisor of A and B. This means C divides A and C divides B. And the greatest common divisor is the okay, how can I explain this? Okay, the greatest common divisor, let's say a common divisor D is the greatest common divisor or GCD. So what this means is that if C divides A and C divides B, a common divisor of AB, okay, of A and B. This means if C is a common divisor of A and B, then C divides D. Okay, and so D is assumed to be a common divisor already. So of course D is a common divisor. D divides A and D divides B. So D is a common divisor. And for any common divisor C, we have C divides D. So if this is the case, then this divisor D is called the greatest common divisor. This is just like the way we define the greatest common divisor for integers. So we can define the notion of common divisors and greatest common divisors in general integral domain other than integers. And here's another definition. Again, D is an integral domain. And let A be any element of D, then dA, which is defined as this set XA, where X is any element of D, is called a principal ideal. We already know that this set is an ideal of this ideal of D, and 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 also an integral domain in which every ideal is principal. So an ideal being principal means it is generated like this. So an integral domain in which every ideal is principal is called a principal ideal domain. Principal ideal domain. The principal ideal domain and principal ideal. And as we have said before and explained previously, this dA is an ideal of D, of course. And dA plus dB and AB, A and B are some elements of D, is also an ideal. Okay. And if we say an ideal I is a principal ideal, is a principal ideal, then this means there exists some element in D such that dA is expressed as the ideal I is expressed as dA. Okay, so this is what we mean by every ideal is principal. So every ideal in a principal ideal domain can be expressed in this way. Now here's a little interesting lemma involving principal ideal domain. Let D be a principal ideal domain, and any AB, two elements in D, have a greatest common divisor D given by dA plus dB equal to dD. So for any two elements AB, its greatest common divisor D is given by this. Okay, let's prove this. dA and dB are ideals. Therefore, dA plus dB is an ideal. And since D is a principal ideal domain, so this means this ideal is a principal ideal. So this means there exists some element such that dd is equal to dA plus dB. Okay, so far so good. And we claim that this D is the greatest common divisor. Greatest common divisor of A and B. And first of all, because of this relation, we have dA is a subset of dd. Okay, but the element A belongs to dA, so this means A belongs to dd. So this means this means A can be expressed as some let's say some element, let's say x times d, for some x. Okay, so this means D divides A. So D is a divisor of A, and similarly we can show that D is also a divisor of B. So D is a common divisor of A and B. Next, we show this D is indeed the greatest common divisor of A and B. So let C be any common divisor of A and B. So this means C divides A and C divides B. Okay, and since D belongs to dd, which is equal to dA plus dB, there exists some x and y such that D is equal to xa plus yb. Okay, but since C divides both A and B, so that means C divides xa plus yb, because C divides this and this. Okay, therefore C divides D. So any common divisor of A and B divides D, therefore D is the greatest common divisor. And we are done.